The divergence theorem is one of two integral theorems that we'll discuss in this class, and it is so widely used in a variety of physical applications. It appears in potential field theory, for example, electricity and magnetism. It also is widely used in solid mechanics and fluid mechanics. And just to state what the divergence theorem is, so the divergence theorem states that, let's say we have an arbitrary volume, and the magnitude of the volume, the size of the volume is big V, and it's surrounded by a surface of capital S. So it's any volume of an arbitrary shape of any size, and whatever that volume is, it's surrounded by a surface having a surface area S. So the divergence theorem states that if we integrate over that surface, the flux flowing normal outward of that surface, so n hat is the normal unit vector at each point on S. So one might depict it at a certain point right here. You again, you can, if you were to draw all the n hat vectors, they would all point outward, like, and this volume would look like a porcupine. All those arrows would be pointing out everywhere, normal to the surface. So this is some vector field V, and n hat dotted with V is the component of V that's crossing the surface, normal to the surface, and dA is a small element of the surface. So this describes the net outward flux of this velocity field, or this vector field, out of the surface. And if this were a velocity, this would be a volume flux. And the divergence states that this flux out of the surface is equal to the integral of the divergence of V at each point within the volume integrated over the whole volume. Written in words, it's div V, divergence of V, at each point integrated over the whole volume. So that is a statement of the divergence theorem. And your goal, your sort of learning objective for this video is, after viewing it, you'll be able to use the divergence theorem to explain some basic physical processes. And one example that you'll see in the homework is related to fluid flow. So now I'd like to go through and derive this divergence theorem, and in so doing, help you understand the basic physical processes it describes. So you can see pages, what are they, 792 to 794 for formal proof. But here I'd like to take a heuristic approach. Here's a heuristic, I guess, derivation. Of the divergence theorem. You can look up heuristic if you don't know what it means, but it basically means you're using sort of basic logic and intuitive reasoning rather than being sort of strictly tied to mathematical relationships. Okay, so now let's go back and remind ourselves what the definition of the divergence is. So we wrote the divergence of V as div V, or it's also expressed as del dotted with V, and that's equal to, or it's defined by the limit as the largest lateral dimension of a small volume element goes to 0 of, again, the integral of the vector field V out of the surface of delta S divided by delta V. Okay, so let me explain what each of these terms are. So again, we have our arbitrary volume V with surface area S. And let's say within that volume, we have a smaller element of volume. And we'll call that delta V. And it has a surface of delta S. And B is the largest lateral dimension of delta V. So the divergence is defined as this lateral dimension goes to 0, the divergence is equal to the net flux of V out of the surface divided by the volume. So now let's consider, let's sum the effects of all volume elements in the large volume, capital V. So we would write that mathematically as the sum for I is equal to 1 to, say, n, whatever, however many little boxes there are that contain, that are contained within this volume. It's a sum from I equals 1 to n of the integral over the ith surface, so that's delta S sub I, and again we have the volume flux through that little surface. And if we sum this, we get also the sum for I equals 1 to n of the divergence through each associated with each small volume element, I. And this is strictly true, the equal sign, in other words, is strictly true if we take the limit as the largest dimension of these elements goes to 0. Okay, so let's look at the left-hand side of this equation. So the left-hand side is again the sum of delta S1 of n hat dot V dA plus delta S2 of that same integral all the way out to delta Sn of that integral. Again, these are the fluxes out of all the small little boxes that make up our large volume. So let's consider element I and all the surrounding elements. So for example, if element I is, I could sketch that as a box, for example. And let's say the box, the element above it is I minus 1. The element to the left of it is I minus 2, and so forth. The element below it is I plus 1, and the element to the right of it is I plus 2. And then we would say, so I plus 3 and I minus 3 would be in front, or I should say, and in back of I. I won't draw, so I plus 3, for example, would be sort of in front of I, above your computer screen, and I minus 3 would be behind what I've sketched here. But either way, there are, what are there, 1, 2, 3, 4, 5, 6 boxes surrounding element I. So what I'd like to point out is that the flux delta S sub I of n hat, so the flux described by the is integral over S sub I is the flux of whatever V represents. It's the flux out of element I. So if the V field were sort of radiating outward away from I, then it would go like this. If these are vectors of V, then again, this would represent the flux out of element I. But you'll notice that any material that flows out of I to the right flows into the adjacent element to the right. Any material that flows out of I flows into the element on top of it, and so forth. So the net flux out of element I contributes to a flux into the surrounding elements. That is the sum of delta S I minus 3 plus this delta S I minus 2 all the way out to the sum of the flux through delta S I plus 3. That sum negates all of the flux out of the interior element I. In other words, all the outward flux of I enters other elements. So that contribution, when summed with all the surrounding elements, has a net contribution of 0. That net outward flux is 0. It's canceled by the inward flux into the adjacent elements. And this is mathematically, it arises mathematically because n hat around element I is exactly opposite n hat from the adjacent elements. So when you add n hat dot VDA for all the elements, those that occur on this boundary cancel each other out. So we've shown why this sum, when we just take element I as an interior element, and we sum the contributions of the fluxes for it as well as all the elements around it, we see that the contribution of element I, which is the interior element, cancels out to 0. So in fact, when we sum for I is equal to 1 to n of the integral of all the little elements of n hat dot v dA, all the contributions or I should say the contributions from all interior elements cancel. And the only part that is non-zero, the only part that doesn't cancel, is the net flux out of the whole external surface. And that external surface is the surface of the whole volume. So in other words, this, the left-hand side, is equal to the integral of n hat dotted with v dA over the whole surface S. That's the left-hand side. Okay, so we have our left-hand side, which was the sum of the flux out of each of these little volume elements, and it's summed over the whole volume, and we showed heuristically that the end result is the net flux out of the whole surface of the volume. Now the right-hand side, as you'll recall, was the sum from I is equal to 1 to n of the divergence within each little volume, delta V, delta capital V sub I. And if we take the limit as the largest lateral dimension of that box goes to 0, then this turns into an integral of div V dV over the whole volume. So that's the right-hand side. So we're left with the divergence theorem. If we equate the left-hand side, which was equal to, again, the integral over the surface of the exterior of the whole volume, of the flux through that surface, then that is equal to div V when integrated over the whole volume. And this is our divergence theorem. So I've stated what the divergence theorem is. I've sort of gone through heuristically where it comes from. And so hopefully that provides you with some intuition to enable you to apply it to understanding physical processes, such as fluid flow.